Hello everyone. Today at noon, presenter is Mr. Babatunde. He has over 30 years of experience in agricultural and environmental engineering. He specialized in developing sustainable material from agricultural waste for construction and renewable energy, aiming to create eco-friendly alternatives to traditional materials. While fostering education and research in the field. He is also the winner of the UniSQ 3-Minute Thesis Award for 2024. Today, his presentation topic is evaluating the impact of manufacturing parameters on properties of sub-hab bio-composite. Let's welcome Babatunde and hand over to you. Thank you.
Yeah, thank you. Thank you for having me. I hope my screen is being shared now. I don't know.
Yeah, we can see your screen now.
Okay. All right. Yes, like the introduction says that my name is Babatunde. So I'm Babatunde, and I'll be discussing on the topic, which is a part of my PhD research on evaluating the impact of manufacturing parameters on the properties of sunn hemp bio-composite. These are the synonyms of my presentation from introduction, and I will conclude with the recommendation. Now, my introduction. This is my background and the research need. Of course, Australia faces quite a number of housing affordability issue due to high cost of building materials. In fact, about 43% of the cost of the building of a material is what we are contending with. And there is a need for development of a sustainable and cost-effective bio-composite to actually address these shortfalls in housing affordability. And overall, the goal is to have a durable and a sustainable building materials that can fit into the sustainable development goals of having a environment free of carbon emissions. Now, why this sunn hemp? According to the Australian sunn hemp strategic research and engineering plan from 2020 to 2027, they have identified sunn hemp as the material for the future. It has a very high strength and is abundant in Australia, though initially or presently it has been used as a cover crops, using rotating crops and preventing diseases. Specifically, it's used in nitrogen fixation in sugar production. But one of the KPI of this strategic plan is the possibility of harnessing its strength for composite, and that is where I come in and my research come in. At the table before you, you can see relative to other eco-friendly natural fibers, the strength of sunn hemp. You can see the tensile modulus, which is about 25 to 35, and its density is about 1.2 to 1.6, comparably with other diameter. And you could see the pictures of sunn hemp far left, and the major component of it, the bast and the hod. My literature review, a lot of work has been done regarding hemp, but specifically sunn hemp. A few work have not been done, but in terms of the hod usage in hemp, researchers like Xiao Eta in 2024, they have worked on hemp and the particle site. They were able to look at the impact strengths, and their result shows that the impact strength increased with the hemp particle site, as well as but the tensile strength and elongation at break slightly decrease. And these are their findings. You could see the SM image of the morphology of the image of the part of the board using injection molding. Also, another researcher called Darcy et al. In 2020 actually worked on bast fiber for hemp. His result shows he used about 40% weight hemp fiber. This actually results in increased thickness, the impact strength also, and the water absorption. And generally, it has a high modulus. And so he used a BIOS fiber and BIOS base HDP to look at the mechanical and thermal properties of bast fiber. In my work, I'm using sunn hemp, and I'm using different fiber forms. I'm looking at the forms in three. Basically, hemp has two major parts, the odd and the bast. And the third component is like a hybrid. So I'm looking at the effect of these fiber forms with bio-epoxy using a compression molding, to produce bio-composites. I use what we call a response surface methodology to optimize the fiber form and the bio-epoxy resin. And these are the properties, the mechanical properties the responses. I'm looking at the tensile, flexural, and interlaminar. The tensile and flexural has to do with the fiber, while the interlaminar has a great influence on the bioresin. The table below is the parameters and their range or the levels I use. The manufacturing parameter and concentrations are molding temperature, molding pressure, molding time, and the fiber form. There are several types of or applications within the response surface. I use specifically the D optima, and this optima make me to categorize. I have what you call the categorical factor and the numerical factor. If you can see, you cannot quantify the fiber form, and you can see from the table I have hot, bast, and hot bast, which is a hybrid, the temperature range and the pressure range and time from low to high. These are chosen based on extensive literature search, and for the temperature, the TG of the bio-epoxy actually help in determining those ranges. I would like to briefly give you an overview of what is response surface. It's a statistical approach for complex system where you develop and optimize the system. It actually shows the relationship between what you call the independent variables, which you call the input variables, and dependent variables, or you call the response. Here, my independent variables are molding temperature, molding pressure, the molding time, and the fiber form. While my responses are the mechanical properties of flexural, tensile, and interlaminar. You can see that is the D optima, the impact factors. You could see the area shaded are those input factors. You could see the input factor 1 and 2, and the response surface equation is shown below with all the parameters like the independent input, and which I have actually enunciated earlier. Now, one of the key things about response surface modeling is what we call the model, validity of the model. So for me to validate the model, I use what we call the ANOVA table, which you can see. This is the ANOVA table. You could see the tensile, the flexurals, and interlaminar. If you look at the last column, which is the R square, it is very key. It's one of the properties or the parameters for checking how robust or how accurate the model is. You could see the R values, that are 0.9, between 0.9, 0.93, 0.92, 0.87. This means that when you have a value very close to 1, it shows how reliable your model can predict the parameters in questions. So also you can see the F value, the P value, which is less than 0.1. These are indications of the validity of the model. Now, to also validate the model further, I look at the plot of residuals. Yeah, on the figure 1 is the plot of the residuals for tensile, flexurized, and interlaminar. And you can see the normal distribution. You could see all the distributions align directly on the line. They are very close. And this supports the assumption of normality in the model. While figure 2 is the comparison between the predicted and experimental value. You could see the data point aligns well, showing an agreement between the experiment and the predicted results. And this actually confirms the effectiveness of this model in optimizing sun hemp reinforced bio-composites. Now, these are the model's equation generator, right? You could see the responses. Looking at hot bars, these are the fiber forms. The responses are Y1, Y2, and Y3. That is my tensile. Y1 is tensile, Y2 is flexural, and Y3 is interlaminar for each of the fiber forms. And the model corresponding model equation is given. K is a constant. Your X1, X2, and X3, they are my independent variables. That is the fiber forms, molding temperatures, and molding pressure. So these are the design equations in questions. Now for my results, I will be looking at the first result here is the effect of the categorical and numerical factor on tensile strength. I'm talking about, when I say categorical factor, I'm talking about the fiber forms. You could see figure 3 shows the tensile strength behavior of the sun hen composites with different fiber form. You see the bars has the highest tensile of about 7.19 megapascal, which is about 35% more than those of odd and the hot bars. And comparing that value with the value of my resin, which is around the tensile strength of the resin is around 54.9. That shows the sun hemp can act effectively as a reinforced material, not as a filler. Looking at figure 4 is the 3D plot of tensile strength for fiber form. It shows how the parameters, I'm talking about those categorical factors and numerical factors, actually affect the tensile strength. You can see the bars form has the best properties in terms of relationship, in terms of looking at those parameters, looking at the pressures and how the pressure and temperature interplay, how time and temperature, how did they affect the tensile strength as well as the time and pressure. Same goes to the figure 5. You see that is the 3D plot when you are using hot, right? That's how hot fiber, and the figure 6 is about the plot of the tensile strength for the hybrid form. The next slide talks about how the effect of category factors and numerical factors on the flexural properties. You could see from figure 7, that is the strengthening behavior. How does this affect the flexural? The flexural strength of the hot fiber and the bast fiber happens to be the highest with about 91.4 megapascal. This is quite compared to other materials, other natural fibers, sorry, is quite encouraging. And figure 8 talks about the 2D, or what we call the contour plot, that shows the flexural strength of bars using, in combination with the factors of temperature, the pressure, and the time. And 8 talks about the bust, while 9 actually give us the contour plot for the odd, and figure 10 is about the hybrid, which I call the odd bust. So generally, you could see that later in my slide, I'm going to show you how those parameters has a way from affecting these properties. These are images from this SAM, which will be shown later. Now, this slide talks about the effect of categorical and numerical factor on the shear strength of the composite produced using sun hemp, different forms of sun hemp fiber, and a bio-epoxy. Figure 11 is the short beam stress diffraction behavior of sun hemp. The interlaminar shear is around for bars as well. Bars is also very higher than, is the highest among them. Compare, you can see the deflection. Deflection is around 1.2, while for hot has the hot bars has the lowest, which is around 4 megapascal. And also figure 12, 13, and 14, they all shows the effects using response surface. They show the effect of the manufacturing parameters on the interlaminar shear. Figure 12 talks about the interlaminar shear strength for bars fiber forms. You could see, if you look at the peaks of the graph, you see the dotted point. That shows the optimization of that process, and the same goes to figure 13 and figure 14. Now, this is the failure mode of when I checked them under the SEM. If you look at the figure on my far left, that big hole with a yellow arrow here, this is as a result of high molding temperature for the composite made from hot. You could see the effect of high temperature there. And going down, you see this is the interlaminar shears, this is delaminations, and then you can see the fracture of the fiber, and how the matrix crack. This occur at a very high pressure and a very low temperature. Generally, for the tensile properties, the failure mode is characterized by matrix cracking. You could see some void here as a result of high pressure, and we have visible fiber pullout and breakages. You could see matrix cracking for the flexural here, also case of fiber pullout here, and you could see void with this yellow over, and you can see, but here we could see this, especially this is the bars under the SEM, which give us a very good fiber matrix adhesion. You could see, and similar to this figure C. These are the failure modes observed by under SEM for the composite using different fiber forms. Now, my conclusions, like I said, sun hemp fiber in bars form and in optimal fiber ratio gives about composite strength, and we're able to achieve about 70.4 for tensile and 89.5 for flexural strength. and which this shows that bast fiber form has about 35% higher strength and stiffness value compared to odd and the hybrid, which I mean the hot bast composite. It's worthy to mention that individual factors, I'm talking about the molding temperature, molding time, and the the pressure, they do not have significant effect. But when you combine them with fiber form, their effect is very, very significant. Uh, uh, Using RSN to optimize the conditions, the optimal condition given is at 80 degrees, the molding temperature of 80 degree, about for 6 megapascal pressure for 15 minutes, actually gave the best strength of 70.4 megapascal. The quadratic models that were developed can predict tensile, the mechanical properties with a high confidence interval. We could see from our value of my R, the high confidence of about 92%, 93%, and 83% respectively for tensile, flexural, and interlaminar shear. And in conclusion, and for my future direction, I'm looking at how I can improve the adhesion. That is, I would like to optimize the fiber ratio and also look at the treatment, uh, how treatment can actually, effect of treatment using sodium hydroxide to see how we can improve the properties, and also conduct a durability studies on the material by subjecting them to environmental conditions. I mean hydrothermal conditions, and also these models can improve composite design, reduce costs, and also save times. That is the essence of it. So I would like to thank my supervisory team for their unwavering support, guiding, and valuable comments, the organizers of this seminar. And I would like to conclude with the General Manager of Business Development, Agrofuture Nigeria, which says that with few other products offering the same level of environmentally friendly quality that Sun Hemp does, it remains a promising area of research and investment. Thank you so much for listening.